Click record, and we are up and running. Okay, so in section 9.3, we're going to look at the expected value, and then we'll look at normal distributions, well, not simulations. We're also going to look at odds, just expected value, the normal distribution, and odds. That's what section 9.3 is going to be about. Okay. Let's start with this concept of expected value. Okay. If you recall, back in somewhere in chapter 8, when we were dealing with statistics, we talked about the mean. And we calculate the mean of a collection of numbers using that expression where you add each data value together. That sum is divided by the number of data values that you have, and that will give you the mean or the average of a set of data. Okay, now when we're dealing with probability, we're going to calculate the mean. And this is where we know what the probability is that is associated with each numerical outcome in the sample space. This is what we call expected value. Okay. To illustrate that, let's suppose that you're playing a board game and your piece advances the number of spaces equal to the number where the arrow stops on the spinner shown. So here's the spinner right here, as shown here. And these are the outcomes and their probabilities for 1, 4, and 7. So for the outcome of 1, its probability is 3, 6. For 4, that probability is 1 out of 6. And then for 7, that probability is 2 out of 6. All right, now, if the spinner stops at 4, then your piece would advance 4 spaces. On average, how many spaces would your piece advance on each spin? So let's say we spin the spinner 6 times. Then ideally, we would expect a 1 to occur 3 times, a 4 to occur 1 time, and a 7 to occur 2 times. Okay. So for these outcomes, which are ideal, this is what we would expect to get. Notice that the 1 occurs 3 times. So that means we would expect the 1 to occur 3 times. So that's 1 plus 1 plus 1. The 4 occurs 1 time. So that's why you only see 1 4. And the 7 occurs 2 times. That's 7 plus 7. Okay. Now, on the next line, you'll see that it's expressed as repeated multiplication. See, 1 occurs 3 times. So that's 3 times 1. 1, the 4 occurs only 1 time. That's 1 times 4. And then the 7 occurs twice. That's 2 times 7. And this is all divided by 6 because we spin the spinner 6 times. Now, on the next slide, if we broke apart the fractions, it would be this. 3 times 1 over 6 plus 1 times 4 over 6 plus 2 times 7 over 6. And then if we express each fraction as a product, it would be this. 1 times 3 over 6 plus 4 times 1 over 6 plus 7 times 2 over 6. Okay. And then that 3 over 6 represents the probability that a 1 will occur. And that'll be multiplied by 1. And then this 1 6 represents the probability that a 4 will occur. That would be 4 times probability of a 4. And then 2 6 is the probability that a 7 will occur. So that's going to be 7 times the probability of getting a 7. Okay. So if we take the sum of that and we obtain that probability by multiplying their outcomes and their probabilities, that sum will be 3.5. So that means we should expect the pieces to advance 3.5 spaces per spin on average. Here they're deriving question.
Sorry. So now they're actually doing is the one in the middle there.
Yeah.
The
Here-
last piece they're confusing.
Yeah. Here they're just trying to derive a formula for calculating the expected value, which is on this next slide. So the word mean is going to be replaced with the phrase expected value. So in this definition, let's say we had an experiment that has k numerical outcomes, x1, x2, all the way to x of k, with corresponding probabilities, probability of x1, probability of x2, all the way to probability of x of k. Then the expected value, which we're going to denote as lowercase e of the experiment, is just this. We just take the sum of the products of the individual outcome times its associated probability. That's just basically what that means. So in this case here, let's say you have an organization holding a lottery as a fundraiser, and it sells 1,000 tickets. There are 10 winning tickets, where one winning ticket pays $750, 3 winning tickets pay $200 each, 6 winning tickets pay $50 each. And we want the expected value of a lottery ticket. So in this case, here's a table that shows the outcomes and their associated probabilities for that lottery. Okay. Now it does say that there is one ticket that pays $750. So for $750, the probability of winning $750 will be 1 out of 1,000, because it sells 1,000 tickets. That's 1 out of 1,000. For $200, there are 3 winning tickets that pay $200 each. So that's why it's 3 out of 1,000 for that probability of winning a $200 payout. And for $50, winning $50, there's 6 tickets that pay $50 each. That's 6 out of 1,000. And the rest is 90 over 1,000. That's where the probability of winning nothing. Because if it sells 1,000 tickets, that means there's a total of 10 winning tickets. That's 6 plus 3 plus 1. Subtract that 10 from 1,000, you get 990. So 990 out of 1,000 would win nothing. Okay. So that's what the table shows here. Now let's calculate the expected value. So here, we just do the outcome times the probability, 0 times 990 over 1,000. And then plus 50 times 6 over 1,000, plus 200 times 3 over 1,000, and then plus 750 times 1 over 1,000. And this will give you the expected value of $1.65. Okay. Yes. All right.
Like, you know you're not going to win something most of the time with the lottery ticket.
Yeah, but this is just on average.
What's the computational value?
Hmm.
Why are we doing this? What would we use?
Okay. Usually this, expected value is usually going to be on average, how much money that a person would expect to win if they were to play the lottery. And sometimes those expected values in this case, it could be either a positive or negative number, and it might not be worth, and if it's a negative number, then pretty much it might not be worth playing that particular game if there's nothing for you to gain out of it. Yeah. Any other questions? Okay, take a look at this problem number 2 on the next slide. And I know this right here is a spinner, one with the number 5 and the other one's the number 12. And here we want to use this to determine the expected value of that spinner. Okay, let's find out what their probabilities are going to be. In this case, the probability of getting a 5 and the probability of getting a 12. Yeah, for 5, it'll be 1/4 because that looks like 1/4. So that means the probability for 12 will have to be 3/4. Okay. Okay, so now let's find out what the expected value is. The expected value is getting the outcome of a 5 multiplied by the probability of getting a 5. That's 1/4. And then plus the outcome of a 12 times the probability of getting 12. That would be 3/4. So let's do the math here. Let's see. 5 over 1 times 1/4, that would be 5/4. Plus 12 over 1 times 3/4, that's 36 over 4. And if I add 5/4 and 36/4, that's 41 over 4. And as a decimal, what's 41 divided by 4? 10.25. That would be the expected value for this spinner. So if we were to spin this spinner a certain number of times, usually we would expect to get, on average, 10.25. Okay, any questions on problem number 2? Okay. All right, let's look at this next problem here. The table shows the outcomes and probabilities for a 4-sided die. What is the expected value of the die? And here's that table. So in this case here, let's say 3, 4, 6, and 7. 0.20, 0.15, and then 0.35 and 0.30. Now, I don't know if you noticed this here, but if you were to add these probabilities here, they should equal to how much? Yeah, as a decimal, it should be 100% or 1. Okay. Again, that's going to be another statistics course that talks about this. Okay, so now let's look at let's find the expected outcome of this. So here, E is going to be equal to, we take the outcome multiplied by its corresponding probability. So it's going to be 3 times 0.20 plus 4 times the probability of 0.15 plus 6 times the probability of 0.35 plus 7 times the probability of 0.30. So 3 times 0.20 plus 4 times 0.15 plus 6 times 0.35 plus 7 times 0.30. So the expected value here for that 4-sided die would be 5.4. Okay. All right, any questions about problem number 17?
I'm assuming that die is on the third eye.
It's 4-sided, so normally it's usually 6-sided, but I haven't seen a 4-sided die.
Item 3.
Hmm.
Called caltrops.
Okay. All right, any other questions? Okay, here's another one of those expected value problems. Let me move this down here. A game consisting of, it consists of tossing 3 coins. If all 3 coins lands on heads, then the player wins $75. If all 3 coins lands on tails, then the player wins $45. Otherwise, the player wins nothing. On average, how much should a player expect to win on each game? Okay. Now we're tossing 3 coins. So let's think about this for a moment. So if we're tossing 3 coins, the first would be heads, the second would be heads, and the third would be heads. If it's a fair coin, then the probability of getting a head on the first attempt would be, has to be 1/2, because it's either heads or tails. And the probability of getting a head on the second would be 1/2, and on the third, his probability of getting heads would be 1/2. So the probability of 3 heads, we just multiply 1/2 times 1/2 times 1/2, we'll get 1/8. So probability of getting 3 heads would be 1/8. And it's pretty much going to be the same when we're dealing with tails, getting 3 tails on the first, second, and third coins. 1/2 times 1/2 times 1/2. So the probability of getting 3 tails also equals 1/8. Okay. All right, so from here we can find out what that expected value is. And that's this. The probability of getting 3 heads is 1/8. So the person gets 3 heads, he wins $75. So that's 1/8 times 75. And for 3 tails, it's $45. So the probability of getting 3 tails would be 1/8 times 45. And everything else would be nothing. Okay. So if I do 1/8 times 75, and then 1 divided by 8 times 45, add those two, the expected value would be $15. So if you consistently play this game of tossing 3 coins, the expected value would be $15. Or you should win on average $15. Because there are going to be some tosses where you will get all 3 coins to be heads or all 3 coins to be tails. And on other cases, you might not get, well, you'll get a combination of heads and tails. Okay. Questions on expected value and how we calculate expected value. Okay. Next thing we'll look at is standard deviation. Now, I don't know why they introduced this in probability. Okay, this is part of a statistics concept when we deal with mean and median and mode, and also range, which is a measure of variation. This is also a measure of variation as well, standard deviation. Okay. And I'm going to move this down for everyone to see. Let's say we let X bar denote the mean of the numbers X1, X2, X3, and X4. If you recall, X bar is the mean of a set of data. You take the average of the numbers by adding those data values, divide that by how many data values we have. The measure of spread of those numbers is called the standard deviation, and we use lowercase s to denote standard deviation. And this uses the square of the deviations rather than the absolute value. So here we don't use absolute value here. We use the square of those deviations. And this is the formula for finding the standard deviation. And that is the square root of, and if we had 4 data values, it would be this. X1 minus X bar quantity squared plus X2 minus X bar quantity squared plus X3 minus X bar quantity squared plus X4 minus X bar quantity squared. That sum will be divided by 4. Okay. Now, that might look a little strange and it might look a little confusing, but we can calculate the standard deviation using this formula. And in this next example, it does break down how to do this. Okay. Let's say Wally grew 4 sunflower plants. The heights were 171.6, 174.6, 174.4, and 175.4. Here I want to calculate the standard deviation of the heights of sunflower plants. So first of all, we need to calculate the mean or the average. That means we need to add those 4 data values and divide by 4. And that would give you 174 centimeters. So we're just adding these 4 data values together, divide by 4. That will give you the mean of 174. So the first thing you have to do there is calculate the mean of that data set, or the average. And then next you're going to see this. Here, we list the data set, the data, and it doesn't have to be in numerical order necessarily. And then you're going to compute the deviation from the mean. In other words, you're going to take each individual data value and subtract it minus the mean. So for like 171.6, the deviation for that would be that data value minus 174. So 171.6 minus 174 would give you negative 2.4. And then for 174.6, 174.6, its deviation would be 174.6 minus 174, which is 0.6. And then 174.4, we subtract that minus 174 to get 0.4. And then finally 175.4 minus the average of 174 will be 1.4. So these represent the deviations here. And then number 3 is to square the deviations. So we take each deviation and square it. And keep in mind, anytime you square a negative, it's going to be positive. So negative 2.4 and you square it will be like negative 2.4 times negative 2.4, which is 5.76. And then 0.6 squared would be 0.36. Then 0.4 squared would be 0.16. Then 1.4 squared would be 1.96. And then step number 4 is to sum the squares of the deviations. That means we add the square of the deviations together to get 8.24. And then finally, we compute the standard deviation. That 8.24 will be divided by 4 because in that formula, it does have the 4 underneath it. So yeah, that'll be the end of it. 8.24 divided by 4 would give you 2.06, but you have to take the square root of 2.06, and that would give you 1.44. So the standard deviation for the heights of the sunflower plants would be approximately 1.44 centimeters. Okay, so that's a representation of the spread of heights. Okay. All right, now let's look at problem number 48B. The data set consists of the scores 42, 58, 60, and 52. Now you're given 2 parts. Part A is to calculate the mean, and part B is to calculate the standard deviation. So we got 42, 58, 60, and 52.
What circumstances would you use this versus the MED?
Oh, the mean absolute deviation.
How are they different from each other?
The standard deviation represents the spread of the data, how the data is dispersed out. But with the mean absolute deviation, you're using the absolute value of those. This doesn't use the absolute value. Okay. I know, but you know, I might need to explain more of that probably next class meeting. Okay. That's okay. All right, now part A says calculate the mean. Which is, of course, we're going to use X bar for the mean. So that's basically, we're just adding the 4 data values together. We're going to add 42, 58, 60, and 52 together. That sum will be divided by 4. How much? 53. Okay. So this is 212 on top for the numerator. Divide that by 4, you'll get the 53. So the mean of that data set is 53. Now for part B, they want the standard deviation. Okay. So I'm going to create the table here. The first column would be the X, which is your data set or data values here. And I'm going to list them as I have them. I'm not going to list these in any type of numerical order. Okay. The next column is going to be X minus X bar. That means I take each individual data value and subtract the mean from it. So in this case, the mean is 53. My first X value is 42. So if I do 42 minus 53, I'll write this out. I'm going to get negative 11. 42 minus 53, that's negative 11. And then for 58, that'd be 58 minus 53. This will be positive 5. And then for 60, the deviation there will be 60 minus 53, which will be 7. And then for 52, this will be 52 minus 53, that will be negative 1. And then the next step would be, this is my next column, X minus X bar quantity squared. That means I take each deviation that I came up with, X minus X bar, and square it. So in other words, I take negative 11, and I'm going to square that, which is like negative 11 times negative 11. That's going to be 121. And then for 5 squared, that's 25, 5 times 5. And then 7, we square that, 7 times 7 is 49. And then negative 1, you square that, negative 1 times negative 1, that'd be positive 1. So those are the squares of the deviation. And then next would be to take the sum of these. Okay. So this is 121 plus 25 plus 49 plus 1. 196. Okay. And then that's where I use S is equal to the square root of the sum of these, which came out to be 196. Divided by n, which is going to be 4. Because there were 4 data values here. So what's 196 divided by 4? 49. And then we take the square root of 49, which is 7. This represents the standard deviation of this entire data set. Okay, that's how the data is spread out. Okay, any questions about finding the standard deviation? Okay. Okay, we'll stop right here. Okay, next time, Wednesday, we'll talk about measures of position using the z-scores, and then we'll talk about normal distribution and usual values. And if there's time left, we'll talk about odds in favor or odds against. Make sure that your name, signatures on the sign-in sheet, and for those who are Zooming, do type your name in the chat box so that way you will be counted present. All right, you too.
Read those out of class assignment. It's okay if you didn't.
I bring you one.